Good morning. We are set to finish out Chapter 4. Chapter 4, again, this is such a central part of the course. So many important ideas and concepts that we're working from here. We are relating forces to accelerations. We had looked at this example. We had just done a number of examples, I guess, last class, looking at forces and motion and how they're related. And we had gotten this far. We had gotten to this point where we were looking at these free body diagrams or these force diagrams on objects. So any questions that you guys have from last lecture, stop by office hours and we'll get those looked at. So we had said that here is this boat on some kind of a waterway, and it's being pulled along. Here's a couple people that are pulling with, one's pulling with 40 newtons, one's pulling with 30 newtons. The angles are 45 and 37. And we said to solve the problem, we want to draw some kind of a diagram. And at some point, the diagram needs to indicate what are the forces acting on a particular object. Now, in this example, what we had pointed out was it's really not a complete force diagram yet. They've ignored the gravitational force, which would be downwards. This is a top view diagram. So mg would be what we call into the board or into the page. There's a normal force from the water pushing up, actually a buoyant force pushing up from the water, and that normal force is going to be designated as out of the page or out of the board. Now, we're guessing, since the boat's not sinking and it's not rocketing into the sky, that the acceleration in the vertical direction for the boat, the acceleration is 0. So whatever the gravitational force is, it looks like that normal force is matching. So the normal force and the gravitational force are canceling out. Again, gravitational force into the board, normal force out. And then there's going to be water resistance. So there's going to be some kind of water resistance, and that's going to be opposite the direction that the boat is moving. So if the boat happens to be moving directly forward, the water resistance more than likely is going to be directly backward. So they left those forces out. What they're doing in this example is they're just going to take a look at these two forces alone. They're going to divide those into components, x and y, and then they're going to combine the two x's together. So the two x's are working together in the same direction, and in combination, they're this big. There's that much force in the x direction. The big R here is a resultant force. And in the y direction, what they're calling the y here, now that's not vertical, it's just to the left side. This is to the left of the boat, this is to the right. Those are going to oppose each other, so for those we're going to be taking a difference. So let's take a look and see. Here is the diagram. Again, there's an N and an mg, there's a water resistance. Here are the designations for out of the page and into the page. So a circle with a little dot in the middle says that force is coming out towards you. And a circle with an X in the middle says that force is going away from us. And this is a top view. Here are the magnitudes. And then here is the force diagram with the angles. And what it said to do was, let's look in the x direction and let's combine all of the x components. Now, all of the x components will consist of force A. I got my A's and B's and 1's and 2's mixed up. The text likes to use A's and B's, and I like to use 1's and 2's. Anyway, I think it'll make sense here. So I'm going to use force A and times the, well, that's in my diagram. Theta 1 and theta 2 are here. So force A times cosine of theta 1, that's in the x direction. And then FB times cosine theta 2, that's also in the x direction. Now notice, everything we're doing here in terms of forces, this is 40 newtons and this is 30 newtons. I'm not saying this is, I can't put plus and minuses in here. These are just magnitudes and they're at a certain angle. So the way this works is we're putting in magnitudes here, and we're putting in the angles, and we're adding those together, and we're getting 52 newtons, and we're looking at it and saying, Yeah, it seems reasonable. I mean, the most force we could get in the x direction here would be 70 newtons, right? But the forces aren't directly forward, so we're only going to get a portion of that. So 52.2 newtons, that makes sense. Now in the y direction, same idea. We've got these two forces, one to the left, one to the right. But this time, because of the way, specifically, we've defined the angles here. So with the angles defined here along the x-axis, that says that the cosine components are going to go in the x direction. The sine components are going to go to the side. So the x components are adjacent to the angle, and the y components are opposite the angle. And that's what cosines and sines definitions are. So in the y direction, we're going to have sines. Now what's important here is paying attention to the plus and minus signs. How do I know whether to put a plus or minus sign in here? And I get that from the diagram. So it's not just formulas. If we ignore the diagram, we really don't have a very good way to solve this problem. We really depend on the diagram, and we depend on the diagram being drawn accurately to be able to write down the formulas. I'm looking at the diagram, and I'm saying the two x components combined, that gives us a plus sign for those two x components. I'm looking at the diagram, one force is to the left, one force is to the right, so I'm going to take what's in the positive y direction and subtract off what's in the negative y direction and put that minus sign in by hand. So I have to be able to read the diagram and know if it's a plus or minus sign for those situations. Now taking these, oh, that's still a the minus sign got dropped out, I apologize. So this is a minus sign right here, that needs to get added in. Taking the difference, it says we do have a leftover force. So the way that these two people are pulling on the boat, the person on the left bank, is kind of pulling the boat more in that direction. So there is that leftover force. Okay, and I think we saw that, just to review, let me go back to that picture they gave us. So here is that leftover force. But in any case, that's the idea. This is a very good example in terms of dividing forces into components and then adding the forces in the x to get a net x, and then adding the forces in the y to get a net y. All right, so here's another example. This is some ice. This is a hockey puck. And it says the hockey puck is sliding at constant velocity across a horizontal ice surface assumed to be frictionless. So you notice we do a lot of examples that are frictionless. We're going to take a more detailed look at friction in Chapter 5. And so for now, we're just kind of getting used to how these force diagrams work. And if friction's kind of a bother, we just ignore it for now. So this is a hockey puck on some ice. And it says that it's sliding at constant velocity. It's frictionless. Which of the sketches is the right free body diagram for the hockey puck? Now, well, let's take a look and see what forces we've got. There's a gravitational force. This is mg. And there's a normal force, and I'm going to write that as little n. So I've got a little n and an mg vertically, and they're opposing each other. So I got this normal force, and I got the mg here. Now, it says it's at constant velocity. So here's constant velocity. Constant velocity says the acceleration is 0. So I see this hockey puck, and it's going across the ice at this really high speed, but the speed is constant. And that means the acceleration is 0. And that says the net force in the x direction is 0. So we don't need a force to maintain constant velocity. In fact, constant velocity tells us there is no net force. So we don't need this additional force here. This looks like the right picture. The hockey puck's going across. There is no friction, so there's no need to maintain a force to keep it moving at a constant velocity. And then here, slowing it down, I think it's the one in the middle. I'm going to go with that. We don't need any force to keep it going. As long as there's no friction, we don't need any force to maintain constant velocity. All right, here is a mystery box. So this mystery box, I think, is going to show up several times for us. It's not going away. It's the one that kind of looks like an envelope from the side. Here is a mystery box. It's sitting on a table. We're pulling on it. There's a tension force right there due to that string or that rope that's attached right there. And that's angled at 30 degrees. And so the box itself is 10 kilograms. Okay, there's a lot of words here, but what we're really doing is this. The box is 10 kilograms, and the force is 40 newtons, and it's at an angle of 30. So what I'm trying to do is I'm dangerously skimming the problem. You're not supposed to do that. You're supposed to read it very carefully. But the values that look like they're relevant, there's a mass of 10 kilograms for the box. There's a force of 40 newtons, and that force is angled at 30 degrees. So looking at the diagram here, now is the surface frictionless? Don't know. So I don't see anything regarding friction. So we're putting the normal force in, we're putting mg into our force diagram, and here is that force of 40 newtons. Now we'll see if these are all scaled properly. Let's take a look at what the forces are going to be. So here's the box, there's the mass, there's little n, here's mg, here is tension, I'm going to call that, and here is the angle. The tension is 40 newtons, the angle is 30 degrees. Now I want to find out what these other forces are. So m is equal to 10 kilograms, and once we know the mass and the gravitational field, we can calculate the gravitational force. So the gravitational force will be given by mg, and the gravitational force works out to be 98 newtons. So I've got 98 newtons of gravitational force. Does that mean the normal force is also 98? And in this example, it's not. Okay, so we've looked at some easier examples where n and mg were the same value, but this is more complicated. We've got an angle at which this tension is being applied, and that says that the tension needs to be divided into components. So I'm going to take the tension and replace it. Take out the tension force, replace it with its components. Now this is Tx, and Tx is equal to T cosine theta. See how the angle is adjacent to the x-axis. So since the angle is adjacent to the x-axis, the x component of the force will pick up the cosine theta. The vertical component of tension is opposite the angle. That's going to pick up sine. So I'm going to draw this rectangular box around the tension force, and one of the sides of the rectangle will be horizontal, the other side is going to be vertical. Horizontal component is going to be T cosine. The vertical component is going to be T sine theta. So one diagram here, and then we redrew it with the individual components. If it all works in one diagram, that's fine. But often, especially when you're learning how to set these things up, you know, once this diagram gets cluttered enough, move on and try redrawing it. Leave some stuff out so it's not as cluttered. I hope we left out the box on this side. This is just the forces. All right, what can we calculate from this? Well, what are the accelerations going to be, and what are all the forces going to be? We know mg. Mg we've got, but let's go in and take a look. Let's bring in Newton's laws of motion and say that the acceleration in the x direction, and it does look as if we could have an acceleration in the x direction. So I'm looking in the x direction, adding up the forces, and the forces I have are T cosine theta in the forward direction, and that's it. So I'm pulling on this box. Apparently there's no friction at this point. So friction did not show up in our force diagram. So there is no friction. T cosine theta divided by m. Now the T, we were told, is 40 newtons, and the theta, we were told, that was given information, 30 degrees, we divide through by the inertia of the package, and that gives us an acceleration. It's a pretty good acceleration, 3.46 meters per second squared. Now see, what your friend gave you this package. If you go back and read that long story, your friend gave you this package, and they want you to try and figure out what's inside. And one thing you could do is you could pull on it, and you could, by that, you could determine what its mass is. Because if you pull on it, and you're not getting much acceleration, it must have a lot of mass. If you pull on it and it just very easily accelerates, then it doesn't have so much mass. So you pull on it, you measure, you calibrate the pull, and you get out a protractor and measure the angle. And from this, you can actually work back and determine what the mass of the box is based on what its acceleration was. We're doing it the other way. They told us the mass, and we're calculating the acceleration. Now that was the x direction. So all of that stuff in part A involved only forces in the x direction. Now we're going to move on to a perpendicular direction, what we're calling y. And that's going to be the vertical direction here. Now what we're guessing, and this might be wrong, is that this force is not going to be big enough to lift the object off the table. The box will stay in contact with the table, and kind of a hint for that is that the tension's only 40 newtons, but I got a downward force of gravity that's 98. So it looks like at 40 newtons we're not going to be lifting this box off the surface, that it's sliding along off the tabletop. So I'm going to say, look, if it just slides along the surface, that's zero acceleration in the y. So in the y direction, the acceleration is zero, and that tells us that the net force is zero, and that tells us that if we add all the forces together, they got to cancel out. Now, saying that all the forces add up to be zero, that means all the forces in the upwards direction exactly match all the forces in the downwards direction. Forces in the upward direction are little n and t sine theta. Forces in the downwards direction are mg. Now, there's always this question, do we have enough information to solve? And it looks like we do. We're trying to solve for what n is. And what we were saying earlier is that, n is not going to be as big as mg because the tension is helping to, at least the vertical component, is helping to lift the box. And that's what we're finding out. We're finding out algebraically that n is equal to mg minus however much the tension is helping out. And so putting all those numbers in, the normal force worked out to be 78. So I guess we should have solved t sine theta separately. I guess we didn't. We could have solved these separately. Those would have been good numbers to stare at and think about. But we're thinking of sine theta. Sine theta is 1/2, and t is 40. So t sine theta is 20 newtons. And so that upward angle on the tension is lifting the box with 20 newtons already. And so the normal force just has to come up with the remaining 78. It doesn't have to provide the 98 newtons of support. So everything checks out, I think. Good example, looking at these force diagrams. All right, the problems. So the intention here is that we've looked at some basic examples, and I hope they're all making sense. If they're not making sense, work through them again. Once you're convinced that you understand it completely, put it aside, come back the next day, and try reworking those problems again. So the problems get a little more complicated each time we move on. So now we've got two boxes, and we've got a couple of cables. We're pulling here with 40 newtons. That's the standard pull, I guess. And then there's another cable or string holding those two boxes together. So they're going to call this box A and box B, and this is 10 kilograms. Ooh, this one's 12 kilograms. So the masses aren't the same. The masses are different. That's okay. We're going to be fine. And then we are pulling directly in the x direction. So the forward direction is where the pull is taking place, and that's at 40 newtons. Now, as far as I can tell from the force diagrams, do we have any friction on this one? And we don't. And was there some hint in the question? They said a smooth table. I think they have to come right out and say frictionless. I think they have to, they can't just say smooth. But we're assuming no friction, or they're assuming no friction from the diagrams. And I think we've got all the information. So we've got all the information that is given. Now what they're going to want us to do is this. They want us to do two things. They're asking us, what will the acceleration of the blocks be? Now, are the blocks even going to accelerate? Do we know that for certain? And we actually do. Okay, the blocks will definitely accelerate, and why is that? And that's because we have a net force. There is a force of 40 newtons forward. No matter how much mass we have here, we're going to get at least some acceleration. Sometimes people go, well, if it's got enough mass, it won't move. Well, it's not specifically the mass. It's if it's got more mass, maybe it has more frictional force. But once we've determined that there will be no frictional forces at all, then there is nothing in this example opposing the 40 newtons. Now I know, but the problem this is, sometimes it feels counterintuitive, and so what you have to remind yourself is frictionless surfaces, we just don't have much experience with those. Now we're using frictionless surfaces to keep the problem simple. Eventually we'll get to where there's friction pretty much in every problem. But why this feels a little unintuitive is because you're thinking, but wait, if these get large enough in mass, isn't that going to make it impossible to accelerate? And you go, no. The mass itself, no matter how large it gets, will not prevent the acceleration. The acceleration will get smaller, but there will still be an acceleration. This 40 newtons will still be able to accelerate the boxes. So let's take a look at how to set this problem up. One of the other really nice features of this problem, something that one of the most important takeaways, is that should I treat this as two objects or should I treat it as one? And it turns out it depends on what the question is. The first question they ask us was, what will the acceleration be? Now, if I take a look at the setup here, when I start pulling, when the person pulls on this, the acceleration of box A and the acceleration of box B, they're the same thing. The two boxes are going to move together, they're going to slow down together, they're going to pick up speed together. I can treat those as one object, if I want to, if I need to, for part of the problem. And it does turn out, for the first part of the problem, where they're asking about the acceleration, well, the acceleration is going to be the same for both. I didn't put subscripts, I just said, hey, acceleration, acceleration, same thing. For part A, let's treat it as one object. Now I can treat it as one object, accelerating at some value. The net force acting on the two objects combined is just this force. Now what you're saying is, well, wait a minute, what about the tension between the two? There's a tension on block 1 pulling it back, there's a tension on block 2 pulling it forward. If I'm treating this as one object, this system of objects, as if it were one, I don't have to include those internal forces. So that can cancel out. We can treat it as two objects, and then for the inertia, we'll just combine their mass. So it's equivalent to having a net force of 40 acting on a mass of 22 kilograms, and the acceleration will then be 1.82 meters per second, and that's the acceleration for each of the boxes. Okay, so that was the one object approach. Now in the second part of the problem, they say how much tension is there in that cable. We can no longer treat it as one object if we're going to ask questions about those internal forces. So to answer part B, we have to now separate it into two separate objects so that the tension force now appears in the formulas. So when I set up the force diagrams, the tension force will now show up. So if I just think of object number 1, well, it's got a gravitational force, m1g, and it's got a normal force, n1. Now, it's object 1 that is experiencing the 40 newtons. There they are. So those are the masses. Here's the 40 newtons. Now I've got them separated into two separate force diagrams, and the 40 newtons is acting on block 1. The 40 newtons is not acting on block 2 directly. So instead, what's acting on block 1 is the tension, and whatever tension is pulling back on block 1 will be the same tension pulling forward on block 2. And that's because we're assuming that the string, or the cable holding them together, has insignificant mass. And so it doesn't require any force to accelerate the string. So in that case, we can treat this as a force pair. The tension throughout the cable can be treated as a force pair. The force of block 1 pulling block 2 matches the force of block 2 pulling block 1 in the opposite direction. So I don't have two things to solve for, I have one. And that's an important question when you're solving a problem. Because if the two tensions were different, we don't have enough information to solve. But it turns out they're not. The tensions are the same on both. So I can write down an acceleration formula for block 2. Block 2 in the x direction is exclusively just tension, and then I divide through by its mass. And then for block 1, it's going to be the forward 40 newtons minus the tension divided by m1. So those are just formulas at this point. Now I can take those formulas. Let's see if we can. So what I'm going to do with these formulas on the next page, I'm going to solve for, well, I think I'm going to solve for t. We'll see what the algebra looks like. There's actually, in order to solve for t, what we want to do is, well, it's a couple different approaches. I guess we could solve for t here, or we could solve for t there. That would certainly work. So I can take those formulas and solve for t from each of them, and then I can check, I can double check and see if I'm getting the same answer. There's also a way we can, let's talk about it more on the next page. So taking that formula we had on the left and solving for tension, that says m2 times a, that says 21.8 newtons. If I take the formula that was on the right at the bottom and solve that one for tension, that one gives me F minus m1 times a. There's my F. Here is my m1 times a. That also gives me 21.8 newtons. That's not deriving the third law. It's just checking our calculations. We've already assumed that the forces would be the same, and now we're just checking back to see if the algebra, if we've made a mistake in the math somewhere. So we did get the same force. That looks good. Now here's a different way to solve that problem. This way I liked. I mean, I was able to, I always like it if I can double check an answer. So that seemed like a nice feature. Another thing we could do, going back to this picture right here, we've solved for ax here. We've solved for ax here. Those are two separate equations. Those could be set equal to each other. I could eliminate the ax's by taking t over m2 and setting it equal to f minus t over m1. So let's try that. So that's what I've done here. I took the acceleration expression on the left and set it equal to the acceleration expression on the right. And then I did a few lines of algebra. T times m1 is equal to f minus t times m2. I'm being careful here. I'm pulling all of the tension terms to the left and moving everything else to the right side. I ended up with this. I ended up with the tension is equal to m2 over m1 plus m2 times f. Now, what's interesting, it's often useful when you carry these out, carry them out algebraically, and then stop and stare at them and see if they're saying anything to you. What this is saying is that tension in the cable needs to be a certain proportion of force, right? There was a total external force of 40 newtons driving this acceleration, and it's this portion of 40 newtons that is needed to make sure that block 2 is able to keep up with block 1. So it's specifically the mass of block 2 compared with the total, that portion. So of the 22 kilograms total, 12 kilograms is in block 2, and I need that portion of 40 newtons, or 0.545 of the 40 newtons, in order to keep block 2 accelerating right alongside. Otherwise, the string snaps. Right, so, and that turned out to be a tension of 21.8 newtons, and it matches our other answer. We just keep getting the same answer, so we're feeling pretty confident. Okay, questions on that? So let's look at some more examples. At this point, it's just examples, and then while you're doing the examples, talk to yourself. Talk yourself through, tell yourself what's going on at each step. That's how you build up the intuition about how to solve the problems. So in this case, we've got an elevator. Here's a big pulley, and we've got an elevator that is 1,150 kilograms. We have a counterweight that's 1,000 kilograms. Now that doesn't quite match, so we are going to need some kind of a motor, something to pull the elevator up. The counterweight doesn't quite do it by itself. So what we're doing is we're setting up force diagrams. Here's the elevator on one side. So this is tension, and then that's the mass of the elevator. And this is also tension here. So the tension in the cable on this side matches this side. And again, what we're doing is we're assuming, in this case, that the pulley creates a negligible effect. And that's something we'll look at in Chapter 10. So in Chapter 10, we'll look at rotational motion. And, once we're into Chapter 10, then we can bring the pulley in and find out what effect the pulley has. Now, even if the pulley is frictionless, the pulley still has mass. And that means it has inertia. And that means that the pulley will have an effect on the acceleration of this system. So in any case, we're not going to have to worry about that for now. I just wanted to point that out, some of the assumptions. So we're assuming the mass of the elevator and the mass of the counterweight dominate, and that the mass of the cabling and the mass of the pulley is negligible. And that leaves us with a force diagram for each of these objects. Now, with the elevator and the counterweight, there's a tension in the cable, and both the elevator and the counterweight are going to be experiencing that tension, and that tension is going to be upwards for each of them. Then they're each going to experience a gravitational force of mg in the downwards direction. So it's kind of one-dimensional. Everything here is what they're calling the y direction. Now, what we have to pay attention to here then is, are the accelerations in the same direction? And that depends on what you mean by same direction. So right now they're saying the elevator is accelerating downwards, and the counterweight is accelerating upwards. Now that's the same amount of acceleration, but one is downwards and one is upwards. Okay. Now if you think of the string or the cable as one continuous path, in some sense they're both accelerating in the same direction. Right? They're both accelerating in the direction that the cable is guiding them, and that cable wrapping around the pulley just kind of redirects the cable. Or we could just think of it as just flat out opposite directions. In any case, on the diagrams themselves, I would say drawing the accelerations. Now draw those off to the side. The accelerations should go off to the side. Accelerations are not forces. Accelerations are not forces. Accelerations are telling us about the motion. So here we go. Here's, and I switched the A's and B's into 1s and 2s. Okay, so I got it set up more familiarly for myself. Here's is mass 1, mass 2, m1g for the gravitational force, m2g here, and I am drawing in the acceleration arrows, and I'm drawing them off to the side. Accelerations are not forces. Accelerations are motion. They're telling me about the motion. Now the elevator, is at 1150 kilograms, and that's because they told us in that problem. The elevator itself is 850, but it has 4 passengers, each at 75 kilograms, and so we're up to a total of 1150. The counterweight is at 1,000. So you can see the counterweight initially was enough for the elevator and a couple of people. It was enough for an elevator and 2 people, but 4 people got on instead, so you're going to have a motor system. Anyway, we're not so concerned. We're going to let this go into, I think we just let this go into free fall. So I'm getting off the elevator, but we're just going to let the elevator go. And we're going to have these pulleys. They're frictionless. There's nothing, no braking system attached. We're just going to let them fall. Now for object 1, which is the elevator, writing down the laws of motion, following the laws of motion, the acceleration equals the net force divided by mass. For object 2, we're doing the same thing. On this problem, we got to pay attention to directions carefully. We have to on all, but in this case, m1g is in the direction of the acceleration. So m1g gets the plus sign. Tension is opposite the acceleration, so tension gets the minus sign. And then, of course, we got to divide through by the inertia of the object. For object 2, it's tension that's in the direction of the acceleration. It's mg that's opposite. So here, tension gets the positive sign, and mg gets the minus sign. And then we divide through by the inertia. Now, when I get those 2 acceleration formulas, what we can do is we can solve each one for the tension, and then we can set those 2 formulas equal. So I solved this for t, I solved this for t, and now I'm going to take the m1g minus m1a and set it here, and then I took the m2g plus m2a and set it here, and set those equal. And then I did the algebra stuff, right? And so I carefully went through the algebra. I ended up with this. I ended up with an acceleration that is m1g minus m2g divided by m1 plus m2. Now, just to point this out conceptually, what we have on top is the net external force. What are the forces outside driving this system? And it's gravity. And the way the cable is set up, in some sense, the gravitational forces are opposing each other. This one's tending to accelerate the object to the left. This one is opposing that acceleration that's taking place, but it's not big enough. So the net force is m1g minus m2g. Now in the denominator, what we've ended up with is the net mass. So it's the net force divided by the net mass, and we go, oh yeah, that makes total sense. I had 2 separate objects. I wrote down the formulas for object 1, I wrote down the formulas for object 2, I was careful with the algebra, I solved for the acceleration, and what I'm finding is, oh yeah, it's kind of like taking the net, it's exactly like taking the net external force and dividing by the total amount of inertia in the system. Okay, now moving on, we can also solve for the tension here. Let's carry this through a bit farther. So now I'm going to put numbers in and actually solve for the acceleration. So I brought out the common factor of g. Now notice this turned out to be a net force of 150 kilogram difference times the gravitational field, and I've got my newtons per kilogram here, and so that's all getting divided by 2150. The kilograms cancel in the numerator, and I ended up with an acceleration that's 0.0698, or about 7% of g. And running the numbers, that turned out to be 0.68, so not too extreme. You're right. You don't want an elevator ride to be like a roller coaster ride. You want the accelerations to be fairly modest, and there they are. Now, what we can do, like we did on the last problem, on this example, again, this was the acceleration expression for object 1. This is the acceleration expression for object 2. The accelerations are the same. So that tells us that the acceleration, or rather we can take these 2 expressions, set them equal to each other, and then I cross multiply. I multiplied both sides by m2, I multiplied both sides by m1, I ended up with this step in my algebra, and then I brought all the t's to the left side, and I ended up with this equation. So this equation says the tension in the cable will be 10,480 newtons. So that's a lot of newtons, right? Now, let's think about what the tension would have to be in order for the accelerations to take place the way that we have shown. M1g is going to be bigger than tension, right? Because the acceleration is this direction. Over here, tension is going to be bigger than m2g. The acceleration is in that direction. Let's check and see if that's the case. The net force has got to be in the direction of the acceleration. And so we're guessing that m1g is the biggest force here, and then tension's in an intermediate value, and then m2g is less. m1g works out to be 11,270 newtons. m2g works out to be 9,800. 10,480, sure looks good. So we could take that tension number, I don't think I have, let me check and see. Yeah, so we could have, before we move on to another example here, we could now take that tension number, plug it back into these formulas, and see if we're getting the same acceleration. So as you know, as I mentioned, when you have time, when you're working on homework and whatever, practice checking your answers. So much of science and engineering involves checking the numbers that you've come up with. It's not like, hey, I calculated it, I'm done, I'm not going back and calculating that again, because I got numbers, and once you got numbers, you're done. You're not done. Once you get the numbers calculated, see if they make sense. Go back and double check, find a way to go back, double check the numbers. All right, here's a piano, and so you think here's a piano and someone wants to put a piano on the roof, oh maybe in that second floor window. So they're going to lift the piano up. This seems it's like something I want to stand back away from. I don't want to stand under the piano. Here's a crane. I hope that looks sturdy. There's a counterweight on the crane. They're going to lift this piano and they're going to pull. Now, if you look at the way the rope is set up, you think, well, that looks fine. There's a couple of pulleys that are helping out. But this pulley system actually is creating an interesting effect. The person pulling on this sets up tension in the cable. And it's not just tension where the person's pulling. The person pulling is going to be setting up tension throughout the entire length of the cable. So that means that the cable is going to be pulling down on the crane with that tension. And more importantly, what it means is if I look at that pulley at the bottom has two tension forces upwards. So by this person pulling with force T, they're actually exerting a force on the piano of 2T. So the person doesn't have to pull with mg, they only have to pull with half. Now you may have seen other pulley systems where the rope gets wrapped around a second time, or maybe a third time. Every time you run the rope around that pulley at the bottom, you're picking up an additional force of 2 times T. So at some point, that person doesn't have to pull with very much tension in order to lift the piano. Now, the downside of this is that if you wrap the cable around a few times, if this person's got to lift this 10 meters, they actually have to pull on the rope much more than 10 meters. So not as much force, but they're going to have to do that over a much longer distance. So that's the way this works. Let's see, what things do they want us to answer here? The piano is 2,000 newtons. Now, they didn't give us the mass of the piano, so that's interesting. They did not give us the mass. They just said flat out, mg is 2,000. Here it is. So here is the piano, and the piano is at 2,000 newtons. Now, what they've also done here is, instead of the force diagram acting on the pulley, they're just treating the pulley as if there's 2,000 newtons pulling down. if we pull the piano up very slowly, which we will, we're not going to, this piano is not going to, it's not going to rocket into the sky. It's not going to accelerate at some amazing rate. We're going to think of pulling this piano up at a constant velocity. So if the velocity is constant, then I've got two t's. That says 2t equals mg, so the tension in the cable only has to be half of mg. If mg is 2,000, the tension only needs to be 1,000. The acceleration we're going to say is 0. We're going to pull the piano up at a constant speed. So that's, that's one worth thinking about. There wasn't a terrible lot of math going on this one, but there's a fair amount of detail to think about. All right, here we are in the car. Now, I would like to see somebody create this effect. So we have to make sure we're not distracting the driver on this. The driver just got to drive. Somebody else has to be paying attention. So we've attached a string and a weight to the top of the car. We've set it there. Here's a plumb bob, and it's right on the vertical, kind of by definition of what vertical is. So it's right on the vertical, gravitational force is pulling it down. What happens now if the car is moving at a constant velocity? And this is the picture, right? If the road is really smooth, then moving at constant velocity is the same as being at rest. And that would say at constant velocity, we don't need a force to keep the ball moving forward. We don't even, it doesn't even have to deal with air resistance because the air is being brought along also. So if I'm driving in a car, perfectly smooth road, and that's where I was a little skeptical here, is in most cases you're going to have, that ball's going to be bouncing around because the road's a little rough. But you find a really smooth road, and no stop signs, no red lights. You got to get away from, where are they driving? Yeah, they're out away from traffic, and the road just goes straight for a long enough distance, and they're going at a steady speed, and the road's perfectly smooth. Then the ball just sits there at rest. There's a tension force upwards, there's an mg downwards, and that's it. That's everything that's going on in this example. Now, how is constant velocity picture different from acceleration? And we're going to say the acceleration is constant. So it's going to be an acceleration of 1.20 meters per second squared. Now, again, I think they've done the A and the B backwards here. I think the easy one is the velocity, and then the more difficult one is the acceleration. But they're going to start off with the acceleration example. So we're going to start with this. Well, we talked about the constant velocity already. So what will happen if the car is accelerating? Then the ball also, if it stabilizes at some kind of an equilibrium angle, the ball is also accelerating forward. So the car is accelerating, the ball is accelerating with weight, and we're going to isolate the ball. So we're going to say what forces are acting on the ball. And there's going to be a tension force. Now, there's going to be an mg, and the reason that we know the string now is going to be at an angle is because we're going to need two components of tension. One component, the vertical component of tension, will be offsetting gravity. And that's what it looked like in that top picture, right? Here, there was tension and there was gravity. But now, in addition to the gravitational force, which needs to be offset, we also need to generate this acceleration. That ball, every object in the car, if it's going to be undergoing an acceleration, needs a force acting on it. And that the ball that we have here, the little sphere, needs a force forward, and that's what it's going to get from the string. So the idea here is, and again, we need a very smooth road to make this work. We're going to need a smooth, oh, I've got the string going the other way. Okay, I'm accelerating to the right. And so here we are at constant velocity, everything we talked about. Here we are now with an acceleration going on, and the acceleration is a fixed value of acceleration. But what we're going to have in this, here's the force diagrams, T, mg, acceleration is 0, T is equal to mg. Here, what we're going to say is that I've got tension pulling on that object with mass m. There's an angle here. Now notice the adjacent side of that theta is now vertical. So we don't have to have theta be adjacent to the horizontal component. In this case, we're going to put theta so that it's adjacent to the vertical component. That's what they gave us. So this is now the cosine theta, and this will be the sine theta. This is the component adjacent to the angle, and this is the component opposite. As I always do, I'm going to put the acceleration in here. I'm going to put an acceleration arrow in there. The forces are all over here, and this tells me where the acceleration is. Now, what I can see from this is that t cosine is going to equal mg because, again, this thing is not rocketing off it's not heading upwards, it's not accelerating upwards, and it's not accelerating downwards, but it is accelerating forwards. So the vertical forces cancel out, and that gives us, in the vertical direction, acceleration is 0, t cosine theta is equal to mg. In the horizontal direction, there is an acceleration, so I'm writing that down, and it is due to the net force. Now, the only force we have in that forward direction is t sine theta. So the acceleration will be t sine theta divided through by the inertia. I can take these two formulas. I can take the t cosine equals mg. I can take this formula and say t sine is equal to m times a. So there it is. T sine is equal to ma. T cosine is equal to mg. And one of the tricks we use all the time in physics and in statics, kind of engineering problems, whenever we have two components, we can take the sine theta component and the cosine theta component. We can take them and divide them, and that will cancel out the force out front. It'll cancel out the magnitude of those vectors. And with t gone, that becomes tan theta is equal to, now on the other side, we have an ma and an mg. The m here is the inertial mass, and the m here is the gravitational mass, but hey, they're the same. So the m's cancel out, and it says that the angle that the string is going to be at, if we can hit that nice steady equilibrium, so the ball's not oscillating back and forth, is given by a over g. Putting the numbers in, everything cancels over here, the units. When we do an inverse tangent, we end up with 7 degrees. Okay, so it just depends on how large is the acceleration compared with how large is the gravitational field. Okay, now one of the most important questions on that one, I know I've jumped to this next one pretty quick. Let me pause there just for a minute. So think about that. Okay, so that angle is going to depend on how much acceleration. If the acceleration goes to 0, which means constant velocity, the equilibrium would be back at vertical. All right, inclines are very important. Count on incline problems showing up. They're certainly in the homework. They're going to be on the midterms. So here's an incline, and here's an object here. Now, again, I think they're saying that this continues to be frictionless. And so the box is going to slide down a frictionless, they should just put it in each time, a frictionless surface. So now if it's frictionless, what we would have, let's take a look at this, we're going to have a normal force, but the normal force is not vertical. If there's an incline, the normal force is going to continue to be perpendicular to the surface. So if the surface is tipped by angle theta, the normal force, which started out vertical, is going to tip by an angle theta. So whatever angle the incline is at, and the incline angle is defined down here relative to the horizontal axis. So theta equals 0 would be level, theta not equal 0, theta equal 30 degrees or 40 degrees, that's an incline. And so what happens is the normal force, which used to be vertical, is going to tip by that same angle. Draw these diagrams, check it out, and you can see that. Now the gravitational force will continue to be downwards. So the gravitational force direction continues to be downwards. Just because you put something on an incline doesn't mean the gravitational force shifts. So the gravitational force continues to be down. The normal force rotates by theta. And you can see the angle theta here, right? So what used to be the vertical direction, the mg is still in the vertical direction, and what used to be the direction of the normal force has now tipped by an angle theta. Now that means that this force needs to be broken up into components. We're going to switch coordinate systems. So what's important with the inclines, what's new here, is that we're going to rotate the coordinate system that we're working in. Instead of having x be horizontal and y be vertical, what we're going to do is we're going to rotate these so that, for our convenience, so that, well, what direction do you think the acceleration might be in for this problem? And the acceleration is going to be along the incline, right? So if this is a frictionless surface and we set this here and let go, it's going to start picking up speed down that incline. It's going to head down the incline faster and faster and faster. And so if the acceleration is in that direction, more often than not, we want to rotate the coordinate system so that the acceleration is exclusively in the x direction. And that'll make the problem easier. So you can keep the coordinate system unrotated, but then you have to deal with components of acceleration, which can be done, but it's just more difficult. So I'm going to rotate the coordinate system. Now, when I look at this diagram with the rotated coordinate system, I can see that the normal force lines right up with y. That's good news. The acceleration lines right up with x. Also good news. The problem here is gravity. Gravity is going to have both x and y components. Now we got to decide which of these is mg cosine and which one of these is mg sine. So we draw a rectangular box. Now the rectangular box we draw is going to be rotated. So, and I think I can show that. They're telling us the mass is still the 10 kilogram box. The angle is 10 degrees. So here's the diagram, same one from before, except I'm going to put in arrows for acceleration and velocity, not with the forces, but off on their own. The object's going to be picking up speed, it's going to be accelerating. And then here is the rotation of the coordinate system. This used to be x, this used to be y, but then we took the coordinate system and we rotated the whole thing. This is now x, and this is y. And what we find out is, when we rotate coordinate systems like this to accommodate the incline, both the vertical and the horizontal axes rotate by the same angle. They both rotate by theta. Now if I take a look at that rotated coordinate system, I can see that the normal force, which is perpendicular to the surface, now lines up with the new y-axis, the rotated y-axis. But the mg lines up with the old y-axis, and so what we have to do with mg is this. We have to draw a rectangle. The rectangular box that we draw around mg has to line up with the new coordinate system, not with the old one. So your picture, when you're drawing mg and you're keeping track of components, needs to look like that. You need to have a rotated rectangle. And so this rectangular side is mg sine theta. This is the component opposite the incline angle. And the mg cosine is going to be along the new y-axis. So stare at this diagram and stare at this diagram, and especially pay attention to how that rectangular box is drawn around vector mg and how that's rotated and what the components will look like. Yes, I could ask you to draw that picture. So definitely on the midterms, almost the first part of any problem typically is draw a force diagram or draw a free body diagram showing all the forces acting on that object, and it needs to be drawn clearly enough that I can see what's going on. okay, that I can see that you clearly understand what the force diagram looks like. Now let's take a look. The x direction, I call them parallel and perpendicular. This is actually just x along the surface. Now if I look along the surface, the forces that I have are mg sine theta. So I'm going to take that mg sine theta component, divide through by the inertia, and it tells me my acceleration along the incline is going to be g sine theta. Now we know that we know the value for g, at least if this is planet Earth. If it's the moon, it's 1.67, but if it's Earth, it's 9.80. And so 9.80. Now since it's an acceleration, I'm going to use acceleration units on g. Even though g is the gravitational field, and I've been using newtons per kilogram, when it simplifies down to an acceleration expression, I can go back and use meters per second per second. Multiply it by the angle, and it predicts an acceleration. Remember, there's no friction. If there were friction, then we would have a force opposite going back up along the incline, but there's not. So with no friction, the acceleration, 4.90 meters per second squared. Now the other thing we want to find here is how large is the normal force? So in the perpendicular direction, which is the y direction here, I should have just put x and y in parentheses here. The y direction is here, and that says that n is going to equal mg cosine theta. There is no acceleration happening in the y direction. We could put subscript x, subscript y. That says n is equal to mg cosine. That's 84.9 newtons. Okay, and so that's it. Plan for incline problems for sure. Okay, so that does take us through chapter 4. Practice these problems, re-practice these problems. These are the, this is the kind of stuff that's going to show up. Now, just going back to this problem right here. So imagine taking a problem like we have here, or some of the earlier examples also, and once we find out what the acceleration is, we can start solving for velocities, right? And so some of the homework problems will include these types of examples. The textbook didn't provide any here with their examples in the slides, but there are definitely homework problems, there are practice problems in preparation for midterms that will include some problems. So once you get to an acceleration problem like this, then they could ask questions like, if this slides 5 meters along the incline, how fast will it be going? And since the forces here are constant, the accelerations are constant, and we can use all of the formulas for constant acceleration. So, and again, this is one of the diagrams that causes a lot of confusion, and the way to get around that is just to work through problems involving inclines. I think there's got to be at least a few in the homework with inclines going on, and practice drawing those gravitational force diagrams. All right, so let's wrap this up with chapter 4. And as we talked about, chapter 5 is going to be kind of more of the same. We're going to bring friction in, we're going to bring in circular motion, we're going to bring in air resistance, and we're just going to get more sophisticated in terms of the kind of the level of problems that we're able to solve for. And it's fun, right? Because the problems get to be more and more realistic as you build up this set of skills. So again, read the problem carefully. As you guys know, I don't always do that. That's one of the things I always have to remind myself. If I'm looking at a problem, I got to slow down sometimes, read the problem, identify all the given information. Some of it you might not use, but most of it you probably will. So draw diagrams. Draw a sketch, draw a free body diagram, something that has all those forces. Notice that in most of these examples that I've brought up, that I'm drawing a diagram of what's going on, and then I'm drawing a force diagram with all the forces, and then I'm putting in arrows for acceleration and velocity. I think that's key. I think making sure, because when you draw the velocities and accelerations in, those help you to realize, is it speeding up, is it slowing down? Anyway, I think that's an important part. Choose coordinate systems for convenience. So if downwards is positive, works well, go ahead. Develop some flexibility with coordinate systems. So downwards can certainly be positive. The other coordinate system issue that comes up are those inclines that we looked at in the last example. So, and we looked at that in some detail. So the inclines, also very important. List all the given information and then start writing down formulas. Look in the x direction for each object, look in the x direction, look in the y direction, write a formula for accelerations and forces in the x, write a formula for acceleration and forces in the y. So the approach is fairly systematic. There are kind of these conceptual issues you want to get beyond. The tensions are going to be the same at all locations in a string. The normal force is going to be perpendicular to the surface. Those are the kind of things you want to be practicing. And then solve the problem algebraically. If possible, do everything by algebra first, and then stare at the algebra. The algebraic solution that you come up with will tell you things about what happens under extreme conditions. And then keep track of units. Make sure that your answer is reasonable. Okay? All right, I think I'm going to go ahead and stop there. I'm guessing that there's some questions, so stop by office hours. Let's get those looked at. All right?